healthy product, the organic matter content, especially the more stable humus, increase the capacity to store water and store carbon from the atmosphere. So that's why it can serve as an important carbon sink in the soil. Yeah, here you can see that the stepwise oxidation of organic matter under the anaerobic condition. The anaerobic condition can help to help to increase this process, and also have the ammonification and nitrification. Here you can see that the amino acid can be decomposed to become the ammonia, and then to form the nitrite and nitrate. Nitrite and nitrate are the most important nitrogen formed in the plant, and the complex organic and available protein to make it as simple and inorganic, or the available mineral nitrogen that to increase the soil fertilities that can be provided to the plant growth. And the most nitrogen in the soil is immobilized in the organic composition and is not available for the plant growth, leaching or gaseous loss. So through the mineralization, the microorganism can change 1.5 to 3.5% of the nitrogen each year to inorganic forms that higher plants can use. Here you can see that through the mineralization is a very important process in the soil that have to convert the bit organic unavailable nitrogen pool into the inorganic nitrogen pool to make it can be used by the plant. Can be used by the plant. And the phase of mineralized nitrogen, the immobilization of microorganisms, or the absorption by the plant, as well as the leaching of water. Yeah, the iron formed of the nitrogen, we have these process, and they can exist as the ammonium formed, and a nitrate or nitrite formed. And one is shown as the negative anion form, and then the other nitrate and nitrite will exist as the anion form, and this one show as a cation form. They will combined will be binding with the negatively charged colloids, such as the organic matter, the surface of the organic matter, or different colloids, and still have other anion charge nutrients ion. They will be combined with the ammonium formed in the soil solution, and another nitrate and nitrite. The less of them will be exist in the environment, and because they are not stable, in the soil solution. So they will be charged or combined with the positively charged colloid. The positively charged colloids, not that too much, but still have, and also the soil solution have other positively charged colloids, such as the hydrogen, aluminum, like this. They will have a combination with them. It will have reacted with the mineral to form salt. If they form salt in the soil, will increase the salt level in the soil, and maybe to some plants not that good and will affect their growth. So for the salt and some beneficial elements, I will mention it in the next lecture. And here shows the importance of the nitrogen to a plant. Here I just show a little bit uh, for the nitrogen and phosphorus, because in the next lecture we have some specific talk functions, function discussion, and transportation, as well as the deficiency and toxicity of all the 14 nutrients elements on plants. I will have a further discussion and explanation for them. And here you can see that the nitrogen is important to the plant growth, because it's the first macronutrients shown in the 70 essential nutrients to the plants. The atmosphere can contain 78% nitrogen, but the plants absorb the mineral nitrogen only in two forms, which are the ammonium form, nitrate or nitrite form from the soil. So we said the nitrogen source in the plant majorly come from the soil, which are converted to the progressively to the ammonium amide from protein ammonium uh, to form the amide from the protein. Most protein are enzymes acting as catalyst of the metabolism, and in the integral parts of chlorophyll, molecules and nucleic acids that control the heredity in the plant. And deficiencies of nitrogen can lead to started growth and yellowing, corrosis, where you can call it corrosis, and later I will show you the corrosis, which means that you can see that the leaf becomes yellow color, not, and the first part of showing these deficiencies is in the older leaf or the shoots, and oversupply, the decreased crop maturity, increase the succulence and the risks of disease and the insects attack. Here you can see that too much nitrogen being applied in the soil make the plant is shorter, and make it increase the succulence, and the more insects will attack for the plants. Okay, let's us to take 10 minutes break, then 10 minutes break, and then we'll come back at 11:45。好，我哋剩低嘅等陣先講，我哋10分鐘嘅 break，我哋11點45左右啦，咁我哋先再返嚟。等陣見。 Okay. For the next part is the humidification is known an a unified concept on the humus formation seems to involve the following process: the layering for the water-soluble nutrients for plant residues such as the 19% of potassium lost in the 3 month timely locally. So for the fertilizer application, we can consider for this nutrient release in the soil and nutrient loss in the soil level, and the decomposition of ammonifier and nutrifier result in the release of ammonium and nitrate and nitrite. And furthermore, the decomposition by the ammonifer and lignins are, however, resistant to the decomposition and immobilization of mineral nitrogen by microbes and their subsequent decay, therefore can repeating the decay process. So the humus equals the undecomposed lignin and other synthesized organic substance. And here shows the transformation of organic matter in the soil. And here you can see that the soils, including the litter and roots, the dead organisms, and excrement of living organisms. And they will enter into the soil and decompose as a compressed organic molecules such as the carbohydrate, protein, the lignin, the fat, and other. And it will have the oxidative decomposition, including the humidification, mineralization we mentioned later, can convert it as inorganic forms that can be used by the roots of the plants, the available plant nutrients, and also these iron can be leached out, and also it have a chelation. Chelation, which means that it have a chemical reaction, some specific chemical reactions to form the organometal complexes and make these nutrient iron firmly being retained in the soil level, and this chelation always occurs for the metal ion. So for the heavy metal pollution, they will have the chelation. The chelations reactions and make it cause further pollution contaminations in the soil level. And cat ion exchange capacity, we said most of the nutrients ion exists as the cat ion formed. So they will have easily bind with the nutrients ion with the nutrient ions with the colloid surface or the colloid surface or mineral surface, and divalent cations are attached more tightly than the monovalent cation. Here you can see that because the divalent have a stronger attraction, have a stronger attraction on the mineral surface or the colloid surface. And here you can see that the energy of absorption increase with the valence, but decrease with the hydrated radius of ions. The greater the energy of the absorption, the more tightly the ion is held by the crate. So here you can see that if the roots want to extract one ion from the clay surface, which one will be the first one being attracted by the root or being get by the roots is the sodium, because the higher, as we said, the higher energy of the absorption, the higher valent, the calcium ion, or the other magnesium ion, they have a stronger attraction on the mineral surface. So for this part of nutrient ion, not that easy being extracted or being getted from by the roots from the mineral surface. So the roots need to use more energy to extract the cation from the mineral surface, or the nutrient solution can use other same valence or two more sodium ion to replace this binding sites for the calcium ion, that to replace it, that make it available in the soil solution. This calcium ion can be used by the root of the plant. And the cation energy absorption decreased in the order. You can see that the calcium needs higher energy, and the next one is magnesium, and the following is the potassium and the sodium. The potassium and the sodium, all of them, they are monovalent, so they don't need that high of energy like the calcium and magnesium. So the erodibilities, you can see that it shows a different trend with the energy absorption trend. The cation intrinsic capacity also is the pH dependent process, because it increases with the pH in the most soil. You may ask why the CC exchange, the cation exchange capacity will increase the pH in most soil, because through the cation exchange, the as what I said, the divalent have a stronger or more tightly than the monovalent cation. So which means that the hydrogen ion is more easily to being replaced by other cation, So that's why the more hydrogen ion will be released in the soil solution, that to decrease the pH in the soil. And therefore, you can see the CEC, the cation exchange capacity, is determined at a pH of 7 or above. To that, you can obtain a more accurate result, because the hydrogen, the pH level also will affect the CEC level, the CEC in the soil. So here you can see that different soil type, a different soil texture have a different CEC number. Always the humus have a highest CEC because they have a lot of binding sites for the cations that increase the cation exchange capacity. And here shows the 3 expression weights for the CEC that you need to remember. Is show it can be show it as the mg, the milligram per 100 gram, the milligram per 100 gram soil, or you can show it as milliequivalence per 100 gram soil, or the most common expression way is showing as the centimole per kilogram soil. Yeah, these three expression unit for the CEC you need to remember. And the CEC between the mineral soil in the humid regions and the semi-arid regions, it show the weather, the humid level also will affect the CEC, the characteristics, and other base saturation or the pH. You can see the calcium, the exchange level for the calcium will show the more higher in the semi-arid region. So the weather, the humidity in the soil will also affect these characteristics of the soil. And also you can see that the CEC, it show it as the second one is a milliequivalence per 100 grams of the cation shows a higher CEC in the semi-arid region soil. So here has the question is if the tropical soil of Aussie soil and Arctic soils contains on the average 18% of the kaolin, 20% of the sulfuric oxides, but limited amount of morionite. They have any implications for the soil texture, and if for the soil texture, soil texture, you can know that the structure and the properties for this type of soil. The kaolinite and sulfuric oxides are low activity clays, as we know is 1-to-1 structure for this type of soil. So they have a limited amount of absorbed cation, which means that these type of soil may be limited for the soil fertility, maybe not good for the plantation. And it have the permanent charge larger than the pH dependent charge. Therefore, the cation nutrients are likely higher than the anion nutrients, and the permanent charge larger than the pH dependent charge, which means that most of the nutrients iron cannot be used by the plant. And severe leaching result in a low potassium, sodium, calcium, magnesium, and all these belong to the essential nutrient. And however, they have a high aluminum and a hydrogen level on the exchange side, which means that the soil pH level will show the acidity, and also not enough and less essential nutrients to the plant. We call the pH toxicity, the acid toxicity by the aluminum and the hydrogen. And above properties may change if the ecosystem is disturbed and contained with high soil organic matter whose charge is 100% pH dependence. So you can change the soil properties through the soil organic matter addictions in this type of soil. Otherwise, this type of soil is not good for the plantation, is not good for the soil fertility, cannot support for the plant growth. So from just one soil property descriptions, you can know the more information from it. And another factor affecting the soil pH, we also need to know the balance between the acids and non-acid cation on the soil, on the colloid surface, because the balance between the acid and the base in the soil solution are very important. They can affect the availability of the nutrients, that 14 different nutrients iron in the soil solution. The soil can resist the change in the pH as the buffering reaction. And And because they have the different cations, a hydrogen ion, and other hydroxide ion to resist the pH change. And the change in the chemistry of the soil solution reflects is a consequence of change in the chemistry of the soil solid. And here shows the active and the reserve acidity. The total acidity, which means that the residue and is changeable, and the part with active. Active part, which means that this part is for the pH measurement. When you measure the soil solution, when you extract the soil pH by using the different solution, water or other acid, by water, that you can measure the soil pH is so it's as active acidity. If you want to change it, if you measure the soil pH as an pH 5, you need to add more alkali to balance the soil solution. It will not change immediately because when the active acidity being extracted or being balanced, more is changeable. More is changeable. Hydrogen ion, the acidity cation will be released to resist the acid or alkali balance. So here reserve the acidity depends on the parent material, the texture or the soil organic matter in the soil. So it's difficult to change the pH in a bit area of the soil. If you just want to change a little bit soil in the pot, it's okay. But if you have a farm, large area for it, it's difficult to change the soil pH. You need to think the other method, maybe find a more suitable plant for the plantation. It's changeable aluminum in the soil. You can see that the unique characteristics of the acid soil, and you can see that most of them occupies only have the aluminum ion and hydrogen ion, and that made the soil pH so it in the acidity level. And another more healthy soil condition, you can see that in the normal, in the typical soil level, it have a different cations composition. For example, the calcium, magnesium, potassium, and the sodium, like this. These essential nutrients iron for the plant growth. So in the acid soil, we always call it will cause the aluminum toxicity because it's full of aluminum ions. In these situations, most common serious problem associated with the acid soil. And for this situation, the essential nutrient ions cannot be used by the plants, and only fruits of the aluminum cation. And the plant and bacterial populations are affected, and through the blocking the other essential elements, ions entrance into the plants because they will replace it. And the bind with the potassium, in which inhibit the energy transfer and genetic clothing, and also restrict cells wall expansion. All these are not good for the plant growth. Not good for the plant growth. And really it's a problem above a pH of 5.2. That's why we said the acid judgment and the soil pH maintenance is very important for the soil fertility as well as the nutrients availability for the plant growth. And the acid cation saturation percentage, which means that the acid saturation can be calculated by the exchangeable aluminum ion and hydrogen ion about the total number of the cation exchange capacity. And because you see, if like just for example A and C, they have same CEC number, not that too high, is low CEC number, which means that this type of soil have a poor cation exchange capacity for it, for the nutrients ion or other cations. And you can see that in these two type of soil, in the A type, it have a acid saturation is 17.8%, and type C have a lower acid saturation. And which one is much better for the plantation? The answer is C type, because even though they have a low, both of them have a low CC capacity, and the type A have a higher acid saturation, which means that in these CC number, most of them have 17% of them are occupied by the aluminum and hydrogen. And in the C, only 33%, they are still have 16.6% being occupied by other essential nutrients, for example, the calcium or the potassium ion or the other sodium ion, and these are useful for the plantation. Useful to increase the soil fertility. So if you need to select from these two soil type, you are suggest to select the type C, the same as the B and D, even though they have a high CC number, but this type B is not that good as the type C. Therefore, you can see that the A and B also have a lower soil pH than C and D. So pH is more closely related to the percentage acid saturation than to the absolute amount of acid cations. So also the number of CC also indicate the type of clay in the soil fertilities, that what we need to conserve for the nutrients in the soil, for the plantation of the plant, to judge whether the soil whether the soil have enough nutrient enough for the plant growth. And soil buffer capacity, you need to know the permanence and soluble, and that the soil texture for the soil to buffer the acids and the alkaline capacity, because it will affect for the CC level. And here have a YouTube that when you have time, you can chat and watch the video to see the process for the CC in the soil. And there are 3 ways to measure the CC. So the sums, and the first one is you can measure For different CC determination, when you use different solution, you will measure different parts of the cation exchange capacity in the soil. So the first one, if you want to measure more all the cations in the soil, you can use the sum of the first method. We call it the sum of cation method. That you can measure the number of calcium ion, magnesium ion, potassium ion, sodium ion, as well as aluminum ion after the extraction with the ammonium chloride. Is a neutral salt which does not buffer the pH. That more cation can be extracted by this solution. And in the pure, the crate systems, no other organic matter, and it have a specific or more useful soil type is in the pure clay system. And for example, no other organic matter or the iron or aluminum hydros oxides. And because in these systems, it's difficult to extract more or all the cation from the organic matter. If the soil is full of organic matter, when you use this method, use this solution to extract it, is not that accurate to predict the CEC because they still have more permanent sites in the organic matter. And this is represent CC and the cation on the clay materials, minerals, and it shows the permanent charge CC. And another method used for the effect to predict the effective CC, which means that this part of cation is useful can be used for the plant growth, can be used by the roots of the plants, and this includes the permanent charge CC and the portion of pH dependent CC that is in effect at existing soil pH. That's so these part of CC including two forms, the permanent charge and the pH dependent form, and is determined from the second extraction. Two times extraction by different solution can have a better extraction for different parts of the cations in the soil. So after the same solution, the ammonium chloride extraction, the soil can be washed by the ethanol to remove the soluble, because in this stage you add the ammonium ions in the soil in the system. So you need to use the ethanol to remove the extra soluble ammonium ion, because this part is not showing the actual ammonium concentration in your soil type, and then extract with one more of the one with the sodium chloride to displace the exchangeable ammonium concentration. So the extraction can analyzed for the ammonium concentration in the soil. So different process, different step, a different solution can use for different cation exchange capacity determination. And still have ammonium acetate CEC determination. This includes the permanent charge CEC the all the pH and all the pH dependencies. In the second method, just portion of pH dependencies. So depends on your purpose, depends on your objectives that you can select different method to measure the CEC level in the soil. It's measured by the extracting the soil with either ammonium acetate, but now use different solution for the extraction. You also need to buffer the pH at 7. Then the same posture is following as for the neutral salt CC, and then the in this method the exchangeable aluminum ions should be measured separately because aluminum precipitates as the aluminum hydroxide as a high pH. So different method for the CEC determination and the predicting. You can know the CEC level in the soil, and here shows the sum of the cation can remove all the cation and the total the amount. And aluminum saturation, soil is saturated with the aluminum, and the aluminum is ammonium. The second point is the ammonium saturation. The soil is saturated with the ammonium, and the ammonium is replaced by the sodium, and the ammonium removed is measured. And you can estimate the CC based on the soil texture, because different soil tests, soil content, different soil texture shows different CC level. So from the soil property, soil physical chemical property, you can predict the CC from it, and you can predict the soil fertility, and furthermore you can predict the nutrients level in the soil and the plants. So for the CEC level, you can know which type of soil or which type of plant are more suitable to being cultured in this part of soil. Here you can see that a high CEC value is a good indicator that the soil has a high clay and organic matter content, and it can hold more cation in the soil. And the soil with a low CC is a good indication that a soil is sandy with little or no organic matter that cannot hold many cation. And here you can see that the indication, the high one, more cations, essential nutrients iron can exist in the soil solution. Here you can see the low one, they have low clay contents and low CC capacity, and the fewer position to hold cations. The nutrients iron will easily to leach out, because all the binding site are being occupied by the hydrogen ion or alumina ion, and in these situations, and the soil fertility is decreased. And here you can see that the soil with the high range of the CEC, they have a high clay content, and in this situation they have more have a more bigger balance for the pH change. So if you want to change the pH, more light or acid should be added to correct the pH, and a greater capacity to hold the nutrients in a given soil depth, because most of the soil, most of the nutrients mainly focus on the top 15 cm to ensure the the plant growth, because the most of the plants for the plantation only can reach the top 15 cm. So you just ensure the nutrients level in the top 15 cm of the soil, that is enough. And physical ramifications of a soil with a high clay content, and also have a high water holding capacity in this type of soil with a high CEC range. On the other side, is conflict with the high CEC range. And why we need to learn about the CC is important to the soil fertility, because it can help to characterize the soil and to know the organic matter level. And its major source of negative is electrostatic science, that is a strong correlations between the CC values and the amount of organic matter in the soil. And after talking the CC, there are also another AEC. We call AEC is in iron exchange capacity, because for the essential nutrient iron, not just the cation form, for other macronutrients and micronutrients, some of them also show it as the anion form. For example, the nitrogen always show it as the nitrate, and the nitrite it show it as the anion form. And it's also very important for the nitrogen fixation and assimilation. We will mention it in the following lecture. And also the phosphorus and the boron and the molybdenum, as well as the chlorine, also show it as a negatively charged form. We call it an anion exchange capacity in the soil. Also very important, whether that the soil can hold the anion exchange for these nutrients iron. The nitrogen as the anion form also important for the protein assimilation. It related to the nitrogen fixation, nitrogen transportation, assimilations that can help for the protein synthesis in the plant. And phosphorus is very useful for the roots, flowers, seeds, and fruits. And other boron and molybdenum and chloride also important for the cell division. And some of the micronutrients participate in the macronutrients simulation. Here you can see the molybdenum as the catalyst to process the nitrogen reduction assimilation in the plants. And the chlorine also used for the leaf growth in the plants. Anions are absorbed on the surface of positively charged colloids under acid condition. Because the acid condition, more available nutrients ion, or more available binding size for these nutrients ion, for these anion in iron form. And absorbed by plants is changed with hydroxide ion secreted by the root. So as they change, they can be absorbed directly by the root cell membrane. And the positive charge is associated with the different process. You can see that the first one is aluminum and iron oxide minerals, and they will have fixation for the phosphorus. That's why we said we need to keep the availability of the phosphorus. Otherwise, we will form a non-soluble the solid phase compound with the aluminum oxide minerals and make it unavailable. And the edge of the clay mineral will have a combination, will have a reaction and combination with the available form of these anion sorry with these anion forms of the medium of the nutrients ion, and the soil organic colloids under the acid conditions, namely the carbon groups and phenolic groups, also will affect the anion forms of these nutrients ion. And the anion absorption by the plants. Anion absorption by the plants. The anions are absorbed on the surface of positively charged colloids can exchange with hydroxide ion excreted by roots or microorganism. So here you can see that as a change, and the situation if have a exchangeable hydroxide ion in the solution, then they can help to release the available phosphorus in the soil solution. That's why we need to use the lime. We need to add lime to adjust the soil pH in order to increase the hydroxide level and help to release the still available phosphorus formed in the soil solution that increase the phosphor concentration. Only part of the hydroxide phosphorus can be exchanged. Only part, because some of them are firmly binded and as insoluble forms in the soil. Common anion include the phosphorus, nitrate, nitrite, chloride, and sulfate, borate, and molybdate. And ion exchange capacity is similar with the CC, but it shows the anion exchange forms. The sum of total exchangeable anion that the soil can absorb, such as the chlorine, sulfate, just what I showed you before. These anions are absorbed by positively charged colloids, organic and inorganic, under the acid conditions. And therefore, the ACE can increase with the acidity, and it have a higher in the tropical soil, because the tropical soil, it have a lot of sea soil, algae soil, and secrete oxide, and these all are the positive found in the soil can increase the binding site for the anion exchange capacity in the soil. And also they have the same units for the to represent the AEC with the CEC, centimole per kilogram. Remember, they have three forms to represent the CC or acid in the soil. And preferential absorption in order of phosphorus larger than the sulfate and larger than the nitrate and the chloride, and also related to the valence. As what we mentioned that the divalent have a stronger binding energy than the monovalent, the same as CEC. AEC also the same with the CEC for this point. And the phosphorus strongly absorbed by aluminum octahedron. If you remember, for the soil structure, the aluminum octahedron is very important and occupy a large part in the soil structure. And they are easily and have a strongly binding with the aluminum octahedron to form an unavailable stage in the soil. So it will result in the low bioavailability and accumulation in the soil. And the nitrate expelled that by negatively charged abundantly present in the tropical soil and not even attracted to the soil particles. So it will easily have a littering in the litrates of the after the irrigation. The same also for the chloride. So for this type of AEC, the anion, the nitrate, nitrite, or the chloride easily to be leaching out. So it's difficult for them to retain in the soil. So here you can see that the anion exchange capacity, the number of it is always smaller than the CEC because it's 100% pH dependence and is not caused by the permanent charge. It will not be affected by the balance, by the scene of permanence and non-available binding sites. So 100% being affected by the pH. So the weather, the rainfall for the acid rains and different factors also will affect the CEC in the soil fertility. And here shows the comparison between the AEC and the CEC. Yeah, different charge and absorbed ion also difference, and more for the CEC, and more binding site can be offered to the CEC because the mineral surface, the colloid surface, the organic matter surface also can be provided to the CEC. So the anion have a smaller magnitudes in the soil fertility. However, it also important to the nutrients, to the fertility in the soil, to the nutrients of plant growth. And it is 100 pH dependence charge, and it don't have the permanent charge for the AEC. And for the CEC, they can be affected by the pH, and also the major CEC can be affected by the permanent charge, that we need to know the balance for it. And because AEC of most agricultural soil is more compared to their CEC, so anions such as the nitrate or nitrite, as well as the chloride are repelled by the negatively charged on the soil colloid. So these ions remain mobile in the soil solution and easily to be leached in in the latrate, not easily to retain in the soil. And here you can see that the weathering intensity and decreasing pH, you can show that the effect of weathering intensity on the charge on the clay minerals. And here see more oxide clays, more binding site will be provided to the anion, to the anion, and the if one to one type craze and its mediums can give a balance for the cation exchange capacity and the anion exchange capacity. If the mostly 2 to 1 type craze, which means that it's more cation size can be offered, cation binding site can be offered to the cation, the nutrient cation. So it have a higher cation exchange capacities and also will repel for the other anion binding sites. So the relative importance of pH dependence charge in the clay mineral, and also you can see that is 15 to 100%, 15 to 100 for the 1 to 1 lattice clays. What we have learned for the structure, because 1 to 1 the interface is not that too much space for the binding site, and for the motomorionite is 2 to 1 structure, more gap, more space can be offered to the for the cation. So more of the binding site belongs to the permanent binding site, and so less percentage for the pH dependent charge. pH dependent charge, which means that less of them can be extracted by the plants, by the solution, by the soil solution. So AEC is therefore higher in the tropical soil than in the temperate soil. According to the research by the data collection, you can see. So how do soil colloid work? How does soil colloid work? You can see that the effectiveness of colloid depends on the surface area. As we said, for the kaolinite, motomorionite, from this result we can see that the most area, more nutrients, iron can be held, and the surface charge, the clay, if showing the kaolinite just 1 to 1, mostly negatively charged from the ionized aluminum and the silicas at the edge of particles, and that can be provided for the nutrients iron, and the colloidal carbons have showed negatively charged because of composed carbon side and hydroxide group. And here shows the all iron taken up by the plants. So here shows the preference for the nutrient iron to the cell membrane. Here, cell membrane. Ci, which means that the concentration of the nutrients iron being absorbed by the plants, and the C0, which means that the concentration of nutrient iron exists in the soil solution outside of the plant cell, the root cell membrane. From the ratio, you can see that the potassium ion is more easily easily being absorbed by the cell membrane. And we will have a specific class for the transportation of different ion, because for the potassium you can see that the protein, the cell membrane, it have a specific channel for the potassium. So the potassium are easily is the potassium is more easily to being transported to the from the outside of the cell membrane to the inside of the cell membrane, that being used by the plant. And phosphorus, and here I give you an example to show the phosphorus surprise and phosphorus concentration in the phosphorus concentration in the soil fertility. All the phosphorus in the world are merely supplied by the rock, phosphorus rock, and granule, and limestone waste. Here you can see the what remaining phosphorus. So that's why we need to have a better soil management to ensure to keep the nutrients, the phosphorus level. And here you can see the manure, also another source for the phosphorus. So manure can be challenging to use as a nutrient source because the phosphorus concentration varies widely with the manure type, and manure is a bulky phosphorus source. Solid manures may contain only 5 to 10 pounds of phosphorus per ton. And while the concentration for manure with high water content are even less. So most manure phosphorus is in inorganic forms, and about 16 to 17% of manure is estimated to become available to the first crops after application. So most of them will be leached out, and the manure also is bulky and costly to transport to a distant field, often result in over application of manure to field near the animal feeding operation. Because for the planting farms next to the animal feeding operation, they are more easily to use the animal waste, and will cause the over fertilization for the manure, especially for the phosphorus. Another concern of crop procedures is that the manure application often result in uneven application of nutrient across the field, because the unevenly distribution for the nutrients level in the manure, and also the manure physical qualities and inadequacies of the application equipment or equipment operation. And a careful management is required to achieve a uniform application of manure phosphorus to the land. So the phosphorus rock and the granule is difficult to collect. So the most useful for source for the phosphorus in the plantation is majorly come from the rock. So we need to cherish the phosphorus source in the world. And here you can see that we need to have a better balance for the phosphorus source. And actually million tons of phosphorus released to the environment in the 2000s through the animal manure, and a stricter result in the eutrophication. Because when is overused, being overused, over fertilization, and all the phosphorus will enter into the environment, will cause the pollution, the contaminations in the water environment. So measures to track out the willing phosphorus supply can switch to vegetarian, and for the vegetarian, according to the recently research by the Chinese University of Hong Kong, they found that the people, if they eat more meat, can increase the carbon footprint, the carbon neutral in the world. So they at the in the result for the study, and they found that suggest people to switch to vegetarian. It also can good for the carbon footprint in Hong Kong, in the world. And come back to the phosphorus, and it also suggests to switch to the vegetarian. It can save more phosphorus compared to the meat eater globally. And the recycle phosphorus from the human waste. And this part also very difficult to do it, because there have some pathogen. If you need to reuse it, you need to think about how to remove the pathogens and how to make it as a useful uh, biosolid. And transgenic picked with phytase in saliva to digest, otherwise the undigestible phytase in the feed grain, and the self-fertilizer management. All these um, try to have a better try to maintain a better phosphorus supply and management in the soil and plant systems. And for this table, you can see that it provides an example of such a calculation with a stated assumption. It shows a vegetarian is rated some 0.3 kilograms per phosphorus per year, according to the WHO 2006 study. And if 1/3 of the phosphorus in the vegetarian food is lost during the food preparation, one can assume that the post-harvest material contains 0.45 kilograms phosphorus, assuming that 3/4 of the harvest crop ends up as the organic waste. And the average per capita annual harvest for a vegetarian could have contained 1.8 kilogram phosphorus. Um, and 1/3 of phosphorus taken up by the plants is from mineral phosphorus fertilizer, and the soil phosphorus provides the remaining 2/3. That's 0.6 kilograms of mineral phosphorus fertilizer is required annually for a vegetarian. So here you can see that takes 42 kilograms of the rock phosphorus to produce 0.6 kilograms of phosphorus. So you can see that the production from the rock to the phosphorus, and compare for the vegetarian and the meat-based meat eater, the difference, and how does it less phosphorus fertilizer than a meat-based diet. And returning the biomass from the plant to the soil is by far the most important measure to retain the soil phosphorus in a meat-based diet. Here is the end for today's class. Any questions?咁我哋今日嘅堂咧，咁樣就上到呢度啦。咁樣剩低嗰啲 slide 咧，咁我下堂先再上。咁就大家有冇咩問題？如果冇乜問題嘅話咧，就你哋可以上 Moodle 嗰度揀翻你哋自己嘅組啦。咁樣然之後，我哋應該係年後過年之後先至再上下一堂啦。咁你哋有咩問題都可以隨時 WhatsApp 我啊，或者 email 我㗎，好冇？咁就好啦，下堂再見，希望快啲可以見到大家啦。